The first exercise they have for us is to mark where some particular points would be on the unit circle. So remember, if it's a unit circle, it has a radius of 1 unit. Remember that the circumference is 2 pi r. So if the radius is 1, the distance all the way around is 2 pi. And that corresponds to an angular rotation of 360 degrees. So traveling all the way around the circle, we've rotated an angle of 360 degrees. We've traveled a distance of 2 pi. So if we want to find out where would we be if we started here and went a distance of 5.3, then we would want to convert that into portions of a rotation. So if we have a distance of 5.3, one rotation going all the way around is 2 pi. So if we divide that by 2 pi, the part divided by the whole, then it's going to give that as a percentage, or as a decimal. So 5.3 divided by 2 pi gives us 0.84, or about 84%. So if we start at the initial point and travel 84% of the way, here's 25% of the way, 50% of the way, 75% of the way. So 84% of the way would be somewhere around there. If we take 7.5 and convert that into a percent of a full rotation, divide it by 2 pi, because there are 2 pi in one rotation. So 7.5 divided by 2 pi and get 1.19, or 120%. So if we start here and go 100% of the way around, that's all the way around. And then if we go an additional 20%, 25% would be there. The fourth would be 25%. So 20% would be somewhere in here. So 5.3 would end up there, 7.5 up there. If we did the same thing with 48, so how many full rotations is that? 48 divided by 2 pi, we get 7.64. So that's 7 full rotations. So we go around 7 full times, and then 64% of the next rotation. So that'd be 25, 50, 75 to there, so between 50 and 75. So somewhere down here would be 64% of the way around. So if we go around 7 times and then 64% of the 8th time, we would get to about there. So that's where 48 is. 303, if we take 303 and break that into 4 rotations, if we travel a distance of 303 around the edge, then we go all the way around 48 times. It's about 48.22, meaning that if we go that distance on the edge of the circle, we go all the way around 48 times, and then we go that much of the next rotation. So 22% of the next rotation, which 22% would be about here. So these are just distances traveled along the edge of the unit circle. Now they want us to find a positive and a negative value that's coterminal with this given angle. So when we were finding things that were coterminal in degrees, we would add or subtract a full rotation in degrees. If we have something that's in radians, we would add or subtract 4 rotations in terms of radians. So all the way around the unit circle is 2 pi radians. So if we want something that's coterminal, we would take our angle and we would either add 2 pi or we would take our angle and subtract 2 pi. Now our common denominator is 5, so we're going to have to multiply top and bottom by 5. So that's going to give us negative 3 pi plus 10 pi over 5 for the top one, which that's 7 pi over 5. That's a positive angle that's coterminal. And for the bottom, we have minus 3 pi minus 10 pi over 5, which is negative 13 pi over 5. That's a negative angle that's coterminal with that. So remember what coterminal is. It means that the terminal side is in the same direction. So all 3 of these angles, once they stop along the edge of the unit circle, are at the exact same location. We're just getting there different ways. This one, we're getting there by making a positive rotation. This one, we're getting there by making a smallish negative rotation. This last one, we're making a larger negative rotation, but we're still going to end up in the same place. All right, so if 2 pi radians is all the way around, and 360 degrees is all the way around, those refer to the same amount of rotation. Or if we divide both sides by 2, pi and 180 degrees are the same. So if we're given something in degrees and we want to convert that to radians, if we have degrees on top, we need to put degrees on bottom, and we're converting to radians. So pi radians and 180 degrees are the same amount. Degrees on top, degrees on bottoms cancel. 60 goes into 240 4 times, 60 goes into 180 3 times. So we're left with 4 pi over 3, and the unit for that is in radians. If we take 5 pi, let's convert that into degrees. So if it doesn't say radians, but it's an angle, if there's not a degree symbol, it's understood to be radians. So if we have radians on top, we need to put radians on bottom, and we're changing to degrees. So 180 degrees in pi radians. Notice the pi's cancel and the radians cancel. So we're left with 5 times 180, and the units will be degrees. So that would be 900 degrees. So just using the relationship that 2 pi is 360, or pi radians at 180 degrees are the same. Now, if we have lots and lots of different angles, we would not want to have to convert every single one of them. Here, they want us to name all of these angles, and we don't want to have to take them one at a time and convert all of them. But if we can convert some basic ones, then we can note that the rest of them are multiples of these. If we take 30 degrees and convert it, we have pi on top, 180 on bottom. The degrees cancel. 30 goes into 186 times. So 30 degrees is pi over 6 radians. Normally we don't write radians, so pi over 6. 60 degrees is twice 30. This angle is twice this angle. So if 60 is twice 30 in degrees, then to get the radian equivalent, we can just double pi over 6. Well, if we double pi over 6, we would get pi over 3. That's the radian equivalent of 60 degrees. 90 is 3/30s. So 3 pi's over 6, which would reduce to pi over 2. 180, that's 6/30s, so 6 pi's over 6, or just pi, which we knew that already, hopefully. 270, we could figure that up as pi's over multiples of 30. Or think about this. If we go from here to here, that's 90, 90 more, 90 more. So 270 is 3 90s. If 90 is pi over 2, 270 is 3 of those. 3 pi's over 2. So pi over 2 there. 270 is just that rotation 3 times. Now, 360, if we go all the way around, that's 2 pi radians. 0 degrees, if you don't rotate any, that's 0 radians. And the rest of these are multiples of 45. So if we take 45 degrees and convert it, pi radians over 180 degrees, the degrees cancel. 45 goes into 180 4 times. So pi over 4 is the radian equivalent to 45 degrees. So if we go to here, that's 1 pi over 4. That's 2 pi over 4, or pi over 2. This is 3 pi over 4. This would be 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and then when we get back here, that would be 8 pi over 4. Of course, 8 pi over 4 is just 2 pi. So just by knowing the radian equivalent of 30 degrees and 45 degrees, we can convert all the other ones by just doing multiples of pi over 6 or pi over 4. So often we're dealing with things that are unit circles. But not every unit, or not every circle has a radius of 1. So here we're told we have a circle that has a radius of 90. Centimeters is the radius. And we want to know how many, or what angle in radians has an arc of 168 centimeters. So imagine we got a circle. If we start here and we travel 168 centimeters along the edge, what rotation we go through? Remember, the distance and the angle in radians are equivalent, or are related. So the formula to relate arc length and the angle is S equals R theta. The arc length, in this case 168 centimeters, equals the radius 90 centimeters times theta. So if we divide both sides by 90 centimeters, notice on the left our centimeters cancel. So our angle doesn't have any units. An angle in radians is a unitless angle. This formula only works for theta being an angle in radians. So a unitless angle refers to radians. So we could reduce this. We could divide both of those by 2. We could divide them by 3, so forth. Or we could get this as a decimal. I'm not sure which format they ask for. Let's see, if I do 168 divided by 90, that's going to give me something that has a decimal that goes on forever. So 2 goes into 168, 2 goes into 90, 3 goes into 45, 3 goes into 84, 28, yeah, 28. And then 28 and 15 don't have a common factor. So also notice this does not have a pi in it. 28 over 15 is not 28 over 15 pi. It's just 28 over 15, and the unit on that is radians. So it doesn't have to have a pi to be a radian angle. Now they want that in terms of degrees as well. So if we take 28 over 15 radians and convert that to degrees, we would put radians on bottom, degrees on top. So 180 degrees is the same as pi radians. Radians cancel, leaving us degrees. So we have 28 times 180 divided by 15 times pi. I get about 106.95, or we could call that 107 degrees. And we said it was going to be somewhere there in the second quadrant, so yeah, that'd be about 107 degrees. Oops. So radians and degrees. All right, so here, this problem talks about the speed of rotation. The other problem we did related arc length, which is a linear distance, to theta. Theta is an angular distance. So arc length is a linear distance. Theta is an angular distance. So if we're told how many radians or how many degrees we rotate, and we know our radius, we can find out how far we've traveled along the edge of that circle. But that doesn't tell us how fast we've got there. Have we got there quickly? Have we got there slowly? So if we divide both of these by time, both sides by time, on the left side, we have a distance divided by time, which is a velocity, a linear velocity. On the right side, theta divided by t, that's what angle are we rotating through and what amount of time. So that's an angular velocity. And we use the symbol omega. So v is linear velocity. Omega is angular velocity. How fast is the angle changing? Linear velocity, how fast is our distance changing? Angular velocity, how fast is our angle changing? So one thing we have to be careful with is we have to make sure we have the correct units when we do things like this. So we're told that we have a diameter of 16 centimeters. So let's just sketch real quickly. So all the way across our diameter, 16 centimeters, which means we have a radius of 8 centimeters, of course. We're rotating at a rate of 8 radians per second. 8 radians per second. That's omega. In this formula, notice that where we got that from, theta is an angle that's in radians. And our time quantities just have to match. Our time quantities have to match. So if it's radians per second here, then we're going to have a distance per second here. So V equals R times omega. So our velocity is 8 times 8, so 64. Radians are basically unitless. So the remaining units are centimeters per second. So if our wheel is that size and that's how fast it's turning, then if we were a point on the edge of that and we were rotating along the edge of that flywheel, we were moving along the edge, then we would be traveling 64 centimeters every second. 64 centimeters every second. Notice that's not what we're asked for, though. We're asked for centimeters per minute. So we have to do a conversion. So if we have centimeters per second, seconds are on bottom, so we would put seconds on top. And we're changing to minutes. So in 1 minute, there's 60 seconds. So seconds cancel. So our velocity in centimeters per minute would be 64 times 60, which is 3,840. And that leaves us with centimeters per minute. So imagine that you're a point on the edge of that flywheel. Every minute, that's how many centimeters you travel. All right, here we're talking about the radius of the Earth. So let's draw a circle. The radius of the Earth is given as 4,000 miles. It rotates 1 revolution every 24 hours. So that's an angle. A revolution is a rotation, a turning. So that is and it's also per time. So that's an omega. That's an angular velocity. How fast it's, at what speed the angle is changing. So it's changing 1 revolution every 24 hours. Makes sense? Every day it turns all the way around. So it makes 1 complete revolution every 24 hours. But remember that omega, to use our formula, V equals R omega, omega has to be in radians. You have to have radians on top. So we have to convert revolutions to radians. Well, how do we do that? A revolution is all the way around. So in 1 revolution, well, how many radians are there? How many radians all the way around a circle? Well, if we go all the way around, we've traveled 2 pi radians. So 1 complete rotation or 1 complete revolution is 2 pi radians, also 360 degrees. So revolutions cancel. We could reduce this to with a 24. So our angular velocity, come back. Our omega is pi over 12, and that's radians per hour. Sometimes that would be listed as 1 over hours. So we can get velocity. We take our radius, 4,000, miles. We multiply it times omega, which is pi radians over 12 hours. So V equals 4,000 times pi over 12, about 1,047. About 1,047 radians, unitless. That's miles over hours, also known as MPH, miles per hour. So if you're on the equator and the Earth has a radius of 4,000 miles, then this is roughly what your linear velocity is. Now, we don't feel that because of the atmosphere and so forth, but that's roughly how fast you're moving, just accounting for the rotation of the Earth. All right, the rear wheel of a tractor has a radius of 21 inches. Find the angle, so we're looking for the angle through which the rear wheel rotates in 11 seconds. If the tractor is traveling at 20 miles per hour. 20 miles per hour. Well, that's a velocity. That's a velocity. So our relationship is V equals R omega. If we can find the angular velocity, if we can find how many radians per unit time, then we can find out in 11 seconds how many radians have we turned. So a linear velocity of, let's see, we have to be careful, don't we? Because on the right side, R is in inches. On the left side, velocity is in miles per hour. It would be nice if we could get our time unit in seconds, so that on the right side we had radians per second. Well, these distances have to match. Our radius is in inches, so we really need that in inches as well. So we need to do a conversion. So let's take our velocity, which is in 20 miles per hour, and let's convert that into inches and seconds. So let's do the seconds first. Don't necessarily know exactly how to go from hours to seconds always, but we know in 1 hour there are 60 minutes. And then we know that in 1 minute there are 60 seconds. Remember, we put the same units diagonally from each other, so they reduce. So that gets us down to miles per second. Now we need to get the miles down to inches. So you might remember that 1 mile is 5,280 feet. So that cancels miles out. And then we would need to take feet to inches. 1 foot is 12 inches. So that makes our feet cancel. So that leaves us with inches on top, seconds on bottom. So if our velocity is 20 miles per hour, then let's see what that's going to be in inches per second. So we have on top 20 times 5,280 times 12. And then we're dividing by the result, so parentheses, 60 times 60, close parentheses, or divide by 3,600. So that's 352. So if you're going 20 miles per hour, you're going 352 inches per second. So remember, V equals R omega. So 352 inches per second equals R. R is 21 inches. Times omega. So if we want to get omega by itself, divide by 21 inches. So the 21 inches cancel on the right, leaving omega. On the left, inches on bottom, inches on top cancel. So we've got 352 divided by 21, which that's about 16.76. And that's in 1 over seconds. The units on top cancel, so we're left with a 1 there. We're left with seconds on bottom. That's also known as radians per second because that's an angular velocity. So that's how many radians every second. We're asked how many radians do we rotate if we go for 11 seconds. So take that times 11. We get about 184.4 radians. So with that size wheel, and that tractor is going with a velocity of 20 miles per hour, that's how many radians the tire goes through in 11 seconds. If we multiplied that by seconds, those seconds and those seconds would cancel. We'd be left with radians. If we wanted to know it in degrees, we could find it in degrees.